Let's talk about integrated rate laws. So we're starting here looking at first order reactions. So just to remind you again, this is any reaction where the rate law only has one concentration unit in it like this. So if you have something that says the rate is equal to some constant times concentration of one thing, and that thing is not raised to a power, it is just the one concentration, that is first order. Now, if you remember from way earlier in this chapter, we talked about how the rate is not only equal to some constant times the concentration, the rate is also equal to the change in the concentration over the change in time. So this is one of the very first things we talked about in this chapter. So if the rate is equal to this, and it's also equal to this, then by the, is that the transitive property? I think that's what that's called. The transitive property, the two of them are equal to each other as well. So if A is equal to B and A is also equal to C, then B is equal to C. That's what we're saying here. So if we have this, and we set that as an equation, that is a legitimate mathematical equation. The change, or in this case negative, since we're looking at a reactant, negative the change in concentration of A over the change in time is equal to some constant K times the concentration of A. And while that is a perfectly legitimate mathematical equation, it's not terribly useful to us. It is more useful if we take that and we integrate it, which if you are a calculus fan, you will know what I'm talking about here, but you will be disappointed to hear I am not going to go through the integration. I know, boo, hiss. Everybody wants more calculus in their life, but we're not going to do that here. So if you take this equation and you integrate it, you'll just have to trust me that you get these three equations here that are all really just one equation. So all three of those. These are just three different forms of the same equation. Most often, the one that you're going to see used is this one. This is the most common form of the equation. But the other two are just as legitimate. You just did some algebra to it, essentially. So this is what we call the integrated rate law. Because we took the rate law that we had before, and yes, we did add in a little bit extra there. It's not strictly just the rate law, but we integrated the equation with the rate law in it, and it gave us this equation. Now this particular equation here is only useful and can only be used for first order reactions. So if you have a second order reaction or a zero order reaction, you cannot use this equation. But if you have a first order reaction, this is a very handy equation because it allows you to relate the concentration of a reactant at any time in the reaction to the initial concentration if you know the rate constant. So if you know the rate constant, you could determine the concentration of compound A in this case at every single point along the reaction. You could find the concentration at 1 second, at 2 seconds, at 3 seconds, at 155.56785 seconds. You could find the concentration. It is very, very useful. And conversely, if you know the rate constant, you know how long the reaction has been going, and you know what the current concentration is, you could backfill and figure out what the initial concentration must have been if you didn't know that to start off with. So it's just a very useful equation. Now you might be thinking, well, yeah, you say it's very useful, but you just got done telling us you can't use it for a second order reaction, and those are really common. Well, as we'll see in just a second, that actually has its own equation. But before we get to that, one last thing here about the first order equation. This most common form of the equation. The reason why it's the most common form is because this is what we call the linear form of the equation, because this actually is in the form of y equals mx plus b. So the y is the natural log of the concentration at time t. K, which is a constant, is the slope, or more specifically negative k is the slope. T is the variable x, and then the natural log of the initial concentration, which is what this A naught, that's what we would call that, A naught. A naught is the initial concentration, so the natural log of that is a constant, since the initial concentration can't change. That would be breaking the laws of physics. So that is also a constant. So our two constants, the rate constant and the initial concentration, are m and b, and then our two variables, the concentration at different times and the time itself, are y and x. And so you can actually plot data from a reaction using this equation. And if the reaction is indeed first order, it will give you a straight line, like this one. So one of the big clues, and some of you that have been working through the Crystal Violet lab online have been doing this same thing here. If you plot data for the natural log of the concentration, and I know here it's doing natural log of pressure, but it works for pressure as well. But we're going to go ahead and stick with concentration. If you plot the natural log of concentration versus time, and you get a straight line, that means your reaction is first order. Now, if you plot the natural log of the concentration versus time, and you do not get a straight line, that means you have some other order of reaction. Could be 0, could be second, could be a few others as well. 0 and second are the most common, though. So that's a nice way to work out what the order of a reaction must be just by looking at the graph of the integrated rate law. All right, speaking of the second order reactions, we don't want to have this type of reaction feeling left out in the cold, so we're going to do the exact same thing we did with first order to the second order as well. So we're going to take the rate law for a second order reaction. We're going to plug that in just like we did before. This section here, and actually there's a negative missing there, but like I said, we're not actually doing the integration, so I'm not going to worry too much about that. But if we take this and we integrate it, we get this handy equation here. Notice that it is very similar to this one. The main difference is that in the first order, we were taking the natural log of the concentration, and in this case, we are doing 1 over the concentration. And the other difference is that here it was negative k, so we had the negative of the slope, and here it is positive k. So the main effect that's going to have is first order reactions. When you plot them and they're linear, you get lines with negative slopes, and second order give you positive slopes. That's really the main difference there. So this likewise is a very, very useful equation. It allows us to get a lot of information if we know enough about the reaction. And just like with the first order, we can plot that equation. So this would be our y is equal to mx plus b. So 1 over the concentration at time t is y, t is x. The slope is once again the rate constant, and 1 over the initial concentration is our intercept. And so just like I said before, you get a positive slope with this second order reaction equation, instead of the negative slope that you always get with first order. And just like with the first order as well, if you get a straight line, that tells you that you have a second order reaction. So this particular data, it was plotted with both the first order graph and with the second order graph. And while this one looks kind of straight, it kind of looks like it's straight, you can also tell that there's a little bit of a curve in this graph. But this one is most definitely a straight line. And so this reaction is second order. So then the last one here, we do actually have an integrated rate law for zero order reactions as well. Since zero order rate law is just the rate is equal to k, since you have no concentrations in the zero order rate anywhere, hence the zero order, it just looks like this. Change in the concentration over the change in time is equal to a constant. And so the integrated form of this, and that's just a bullet point, that's not a negative sign. The integrated form of this looks like so. It is the simplest. No 1 over or natural logs or anything like that. It's just the concentration at time t is equal to negative kT plus the initial concentration. And so unlike first order reactions, these just, because the first order reactions, they slow down with time. Zero order reactions do not slow down with time. They just chug along until there's no reactants left, and then they're done. Because their rate is independent of the concentration. All right. We're going to go ahead and call it there for this video, mainly because these 4 examples here are going to take a while to work through. So I want to give them their own video. So in the next video, we will work through multiple integrated rate law practice problems. So I will see you in that video.